Okay, good afternoon, everyone. From both visiting here on site and for both visiting online. Welcome to Tah Poe Seminar Series 51, talk number 3. And today our speaker is Dr. Ninnat Dangniam. And today he will talk in the topic of quantum advantage, classical hardness in correlation games and random sampling. Please welcome our speaker.
Okay, so yeah, thanks a lot for coming, and also welcome to people that perhaps watching this online too. I'm glad to be able to give this talk on site. And well, so maybe I should say first that yeah, so I'm a new faculty. So my name is Ninnat Dangniam, as I was introduced. And I'm a new faculty at IF, the Institute for Fundamental Study here, starting last October. And I have worked on or in the field of quantum information science. And yeah, as a new faculty, I was encouraged to give a talk, like an introductory talk that's hopefully not too technical, and yeah, hopefully that's the case. Although of course there'll be some equations, but yeah, I'll try to give you a little bit of idea of some stuff that I find exciting at a probably relatively rudimentary level. I will not go into really my research, but yeah, I'll talk about something that touched on my research a little bit. Yeah, by the way, when I prepared the talk, yeah, I realized I have to say a lot about this last part about random sampling. So yeah, it'll be really briefly about correlation games, and in fact, it's only one game, so you can ignore the S plurals here. All right. Okay. Yeah, so today we have perhaps starting to hear a lot about quantum technologies and how well or people like to add the word quantum to everything and then say that, oh, it makes things better. But this viewpoint has not been a standard viewpoint at the beginning of the formulation of quantum theory. Or actually, the students were studying quantum mechanics will probably sympathetic with this viewpoint that adding quantum to everything doesn't make it better. Actually, maybe it's make your life mystery. So the old viewpoint is that, well, quantum theory is something of a nuisance. It's a limitation. Well, I want to know what we know, what we can know compared to classical mechanics. For example, particles have no trajectory in the standard formulation of quantum mechanics. You cannot really ask where it is or where it's going before you make a measurement. Like, was it there before you make a measurement? And yeah, as you know, yeah. So this sort of embodied in uncertainty relation, for example. But somehow, today we think of this quantum theory as something that is like a kind of a new fuel, like a new electricity that you want to just put it in everything and hopefully things get better. There's a faster quantum algorithms relative to classical algorithms. They're unbreakable cryptographies and many more. But why is this even possible, or what is like a theory behind it? That's something maybe we will touch on a bit in this talk. All right, so today we are all about engineering for quantum advantage. Maybe it's not some people say quantum information science is not physics anymore, it's engineering, and it's sort of true. But well, okay, let's accept that there's something called a quantum advantage. So what does it mean? It just means that if you compare, hopefully fairly, some classical way and quantum way to do the same test, that the quantum way sometimes you can figure out some way to do better. And there, well, today we talk about a lot about quantum computers and whatnot, but there are a lot of, this has been something that physicists actually thought about for a while, even before all the information science come in. For example, you may have heard of LIGO, that does detection of gravitational wave a few years ago. And one of the really early, that I would say, quantum advantage proposal is actually Cave, my Ph.D. advisor, and he has no relation to Einstein. And he proposed injecting something called a quantum state of light or squeeze light in an empty port of these two arms of interferometer to improve the precision of gravitational wave detection. And for example, I think this day, I just try to find some paper, for example, at GO 600 in Germany, they were able to use this technique to reduce the noise by 50%, so by a factor of 2. And actually, it turns out that that means that you have 2 to the 3. So you have 8 times the observable volume of the universe that you can observe this gravitational wave. So it's quite nice. People talk a lot about, of course, algorithmic quantum speedup, that there are some problems that we believe to be hard classically, or from our experience, we cannot figure out a classical algorithm. But someone clever has figured out, for example, Peter Shor's figured out an algorithm to factorize an integer into its factors in time that is sort of polynomial in logarithmic of the number here. Whereas classically, I think we don't really know any better than to sort of do it in exponential number of steps. And actually, this exponential hardness of the factoring problem is one of the key, or one of the reasons that people use this factoring problem as a cryptographic scheme in like an RSA crypto system, where every time you buy something online using your credit cards, there's something about there's something computer sciencey about this problem of factoring going on. And so it's one of the things that people kind of worry about, that if we can build a large-scale quantum computer, then we will for sure be able to break cryptography. And maybe we have to go to something called post-quantum cryptography and whatnot. Yeah, sorry, the red text here is not really readable, so I just read it for you. But at the present, there's no large-scale demonstration because we cannot build a large quantum computer yet. We can do something like factor 21 into 3 and 7 with 99% probabilities, but yeah, you can do that deterministically on paper as well. And something that has been in the news since 2019, when Google announced this as something they call quantum supremacy, which is basically a demonstration of quantum computational advantage. So you have some computational task that you can sort of prove that no classical algorithm will be able to beat it in the asymptotic, like if the problem is large enough. And that is actually the reason why they're trying to do this experiment, because, for example, unlike factoring, sure, we have a quantum algorithm that is exponentially faster than what we know of classical algorithm today. Sorry if I say that confusingly. We have a quantum algorithm that we know exponentially faster than any known classical algorithm. but there is no proof that that is the limit of a classical factoring algorithm. Maybe tomorrow someone clever will figure out how to factor classically, and then this disadvantage will go away. But the goal of this quantum supremacy is really that to design a problem carefully such that it's a problem that quantum machine can do, but it's like provable that classical machines cannot do. But actually, in the news, you will hear something like, "Oh, Google says that their quantum machine does something that takes like 10,000 years on classical computer." But actually, the meaning, like the comparison with classical algorithm, is not that simple. And actually, this is the part about this provable quantum advantage. This is the part that I will spend most of the time in the talk on. Oh, and then this is the picture of Google quantum computer, just like a large refrigerator hanging from the ceiling. And then this one is another popular quantum advantage scheme using light that China has been doing and has been announcing in the news. All right. So just a little comment. So I talked about a few quantum advantage. What could be called quantum advantage? So I would say that I think everyone will agree that these first two, better measurement and faster algorithms, are useful quantum advantage because the task is designed to do something, whereas this is something that everyone has to talk about when they talk about quantum supremacy, is that this is a useless quantum advantage. It just means what I meant is that the problem is designed for a quantum computer to win. But it's not, I put it in quote because as with a lot of science and technological progress, this is sort of thing that's actually not useless in the bigger picture of things that spawns many technology. For example, the usual example is like the Large Hadron Collider, right? That you just smash particle at high energy together. You don't decide to do anything else for society, but the technological improvement to be able to do that usually just spawn a lot of technology, for example, the World Wide Web, the internet. And in this case also, in order to, for example, Google to do this kind of thing, they do have to have some, to figure out some engineering breakthrough. And so they are useless in the sense, but they are, as usual, they are actually quite something that is nice to have as a milestone, like a technological progress. Okay. And so I just mentioned, well, in the first slide, I sort of put a two contrasting view about, well, some people think that quantum is a limitation, some people think that quantum gives you an advantage. But why, how to actually, what are we actually comparing quantum to? Like, what is the classical thing that we are comparing to quantum? And this is what they call classical foil, which I will talk about. And then I will go to provable quantum advantage. The prototype is Bell's theorem, which some of you may heard. And then really go into what is going on behind this quantum supremacy claim from Google, from China. And before that, I have to give some computational, some primer on computational complexity. It is usually not something physicists care about, just computer scientists. And this will touch on my work just a little bit. Okay, so what is the classical theory we are comparing to? Yes, like what is the fair way to think about quantum versus classical theory? So here I just list, it's just a lot of words here, but here I'm just reviewing what you probably already know this is just the usual rules of quantum mechanics. When you teach it, you have to pull it out from Shankar for students. And that goes the usual story. Quantum state is a vector in Hilbert space. The state evolves according to this differential equation, Schrodinger equation. And there's this weird rule about measurement, where you cannot just look at the state vector directly. You have to choose a measurement. And then when you make a measurement, the system can be found in the state correspond to some orthogonal state with probabilities that are the amplitude square. And then the state is updated. It's found in the state. The state is updated to what you found, corresponding to the measurement outcome. And then another weird rule that physics students maybe don't like where does it come from, is that independent system combine via the tensor product. Another way to say is that the Hilbert space of multiple quantum system combine via tensor product. And if you look at this, and then you look at classical mechanics, they don't seem to really have anything in common at all, maybe a little bit. A classical state is a point in a phase space. There's no Hilbert space. The states evolve, so you just Q saying where you are and P saying at the moment where you're going, and this can be updated using Hamilton's equation. And then there's no rule or measurement. Measurement is trivial. You just look at your system and then you see it. And then the phase spaces combine via Cartesian product. But in a brief minutes, I will argue that actually what we should compare quantum rules to is not really classical physics, but probability theory. So I just rearrange a bit of the quantum rules. I say that a quantum state is a vector of complex numbers. So it just means I fix some basis and just assume we are in finite dimensions for simplicity. And the norm, the two norm or the normalizations of this vector is always fixed, expressed as this 2 norm equal 1. And then there's a measurement rule, the usual measurement rule. System can be found with probably alpha square. But you can, but actually the Schrodinger equation is the evolution that preserve the 2 norm. This preserve the length of the vector. Or more rigorously, for continuous time evolution, Wigner's theorem say that it has to be unitary. An independent system still combines via tensor product. And then I just pull this way of phrasing the classical probability theory. So probability distribution is just a vector, but not of a complex number, not just any real number, it's just positive numbers here. And the sum is always 1. And the measurement rule is no mystery here. It's just you look at the system, it can be found in this state with probably the coefficient in the vector. Maybe I'm a bit cheeky and just use the bracket notation for classical vector. And in this case, in the classical case, the evolution has to preserve the total probability, which is the 1 norm. And actually, which I will show in a minute, that in classically also independent system combine via tensor product. So these are really sound similar. And maybe one takeaway is from this talk is that quantum theory can be thought of just as a generalization of probability theory using 2 norm instead of 1 norm. And a little bit on the tensor product rule if you have never seen it before. So suppose if I just have classical probability, right? So if I have a coin, then it has a probability P of, I flip it and it's being head, and 1 minus P of the probability of it being tail. So if I have 2 coins and I have one with bias P and one with bias Q, then the way that the property combines, so if you throw the two coins instead, right? So now your sample space, we have 4 events. It's just head, 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 tail, tail, head, tail, tail. And you know that the property has to combine like this. And this is actually a tensor product structure, also called a Kronecker product when you compute it. Okay, so okay, so that's the I guess that the stuff I just talked about is just some general stuff that laid the background of everything that is to come in this talk, which is that when we compare classical and quantum test or advantage, it's really not quantum physics with classical physics, but quantum physics with a quantum rule, that's everything that is allowed in quantum mechanics versus everything that's basically allowed in classical probability theory, information processing. And here I will give very briefly a first example in historically of an example of something that quantum advantage that can be proved. And so why does Einstein has anything to do with this? Okay, so we're back to 2 wheels of quantum theories. The wheel of these 2 dogs before, I can argue in a way that this comes from the following 2 different ways of viewing quantum theory. And one is that quantum theory is a classical theory that restricts what you can know. And this is a sort of hidden variable approach, where you say, oh, maybe quantum theory is not really anything new, everything is just, I don't know, random in Gibbs states, and we just actually average over all those hidden variables to get the quantum rule that we have here. And this is something that Einstein and maybe Schrödinger play about, the realists in those days play about, trying to figure out. Another view is that it's something more similar to what I talked about last slide, but it doesn't, the last slide doesn't really prove this point of view, is that quantum theory can be thought of as an extension of classical theory. And so the view is like this. You have a quantum theory here, and depending on your point of view, maybe the classical theory is smaller, or maybe the classical theory is bigger. And yeah, the bigger view is that quantum theory is just a restricted classical theory. And this is, as I mentioned, is something of a hidden variable theory. Yeah, Einstein thought a lot about this, but unfortunately, someone was able to show that not all hidden variable theory would work after Einstein's death, actually. I think John Bell probably proved this in the 60s. And the example is here. So I apologize for some crappy drawing. This is the last slide we just made like 20 minutes ago. So here is another example of a useless quantum advantage. So I will just define some game that doesn't really seem to do anything, but then show that if you have some quantum resource, then you can do something better than any possible classical resource. And so the game is that the game. The players are 2 players, and they play in a team. So they're not trying to win against one another. And at first, maybe you can think of, I don't know, 2 criminals that will be later on be separated and be interrogated with different policies. But the rule of the rule of the game is as follows. So initially, these 2 players can just come to talk and discuss their plan about what to do, and what they're going to do or be subjected to doing is that they'll be separated far away, and then on each side, maybe you imagine there's like a police or inquirer here. They will ask them one question pick out of two choices of question. So maybe you can ask, well, what do you eat today? Or I don't know, did you steal that money? Just like two choice of questions, and these guys don't know beforehand what kind of question that you have to get. And it's the same for both sides. And let me just simplify and say that these questions are just binary questions, so the answer is just yes or no. And so the rule of the game that is sort of purposely designed to try to screw you over is that you would win this game if, for example, so yeah, let's make sure that you understand. So these like 2 point or two like starting points of 2 lines here, I mean just 2 questions. So it's like 2 choice of questions. So there are 4 choices in total. And then these team players will win this game if for this pair of answer, like across the 2 players, they answer the same. Let's say the green line means answer the same. If one say yes, the other has to say yes. The other, if the one say no, the other has to say no. I mean, they can say differently, but then they lost the game. And then I also say that these 2 answers across this line has to also agree, and the same with this. But then if you were asked these 2 questions, you have to disagree. And so this is some toy game that sort of you can see right away that you cannot win all the time. For example, these 2 people can say, oh, I just say yes to everything. And if they do that, if they get asked any questions that are connected by green lines, they'll be okay, right? They'll just win the game according to the rule of the game. But if they ask this pair of questions, then they will lose. And it turns out that that's really the best deterministic strategy that they can do. And they can try to, and each of, that strategy has the probability of winning as 3/3, so 3/4, so you just win 3 out of 4 times, right? You can try to have some probabilistic strategy, like flipping some coins, but if the best deterministic strategy can only go up to this probability, then the probabilistic strategy will also only let you win as just up to 3/4 and no better. And actually, if I didn't have time to write it here, but actually suppose that these 2 people each hold like a quantum spin, like spin 1/2 a qubit, and they're in some maximally entangled state, like the singlet state. And suppose that, and in the setting of quantum theory, these 2 questions would be like the choice of your spin axis that you measure. And there would be some choice, actually, something like on this side, the 2 choice would be maybe measure along Z and measure along X. But on this side, you'll be measure along some axis that is 45 degrees away from X and Z axis, so there are like 2 more choices here. And if you do that, you can calculate that the probability of winning here would be greater than this number. I didn't show it here. But interestingly, this probably doesn't go to 1, even with quantum theory. And some people play around with the idea of post-quantum, super quantum correlation that can win this game. 100% of the time, although it still doesn't allow faster than light signaling. And yeah, so in this kind of non-local game is like a rephrasing of something called Bell's inequality. So inequality here, usually they're written in a different way as an expectation correlation of expectation values of observables. And this is what Bell proved in 1960, that basically if these two people, actually if this like particle that may have hidden variable with them, but the hidden variables are local, meaning that they do not violate spatial relativity. So when so they can have some shared hidden variable here, but when they're separate, one hidden, like one choice of measurement here cannot affect anything on this side. And this is what Bell proved, that if you have any local hidden variable, then this is the best. There's some bound on something, the best thing that you can do. And then, but when you have in quantum mechanics, this can be violated. All right. Any questions on that? Okay. So now I would switch gear and prep you for talking about quantum supremacy or quantum advantage in computational tasks. And if you think about it, this has a very different flavor from quantum advantage of the type that I just told you last slide. Because in there you can, what is really the key of the proof is the locality. So you assume that relativity is true, and therefore you can prove that kind of bound. But here in computational process, you don't really have any notion of separating subsystems or local or non-local influence. And then, so you may be able to guess already that whatever you will see from here will be pretty different. And actually, we have to turn to some complexity theory from computer science to be able to prove quantum advantage in this computational setting. All right. Then I just start with my favorite example. So you may have heard of the problem of 7 bridges of Königsberg. It's some town in Europe, and so the map of the town is like this. You may not be able to see very well where the bridges or where the river are. There'll be some picture later. But one of the hobbies somehow of people there is just to play a game where you challenge the author to say that, oh, suppose that maybe I start at some point in the city. Can you walk through all the bridges without crossing the same bridges twice? And this problem can be phrased in terms of graph, simply, right? So you just think of the bridge as edges and the part of the city that you walk through as nodes or vertices. And then the problem is just can you traverse the graph without crossing the same edge twice? And actually such a tour, so if you start and end at the same point, such a part is called Eulerian cycle, just because later on Euler figured out some simple way to think about this problem. And then here I introduce another problem which sounds really similar. You just swap the role of edges and vertices. And this is something called Icosian game, dodecahedron Icosian game that's made by Hamilton. Actually, this is the same Hamilton that did Hamiltonian mechanics. And the problem is this, can you traverse these edges without visiting the same vertex twice? And this kind of cycle is called Hamiltonian cycle. And so these are like 2 examples of computational problems. Actually, it's also a decision problem. It just asks you whether there is a path. It doesn't ask you what is the path. And in computer science, we are interested, well, like just one instance of problem is not really interesting. You usually think of a general problem where you can input any graph, you can use any graph to define the problem and then just ask the same problem. So for each graph, you call that one instance of the problem. For example, in computer science, when they talk about playing chess, they actually mean playing generalized chess where the board is not 8 by 8, it's like n by n. But interestingly, even though these two problems sound very similar, it turns out that this problem is easy. If an Eulerian cycle exists, then it can be found in about linear steps. I just pulled this out from Stack Exchange. I don't actually know the algorithm. But meanwhile, we don't know, no one knows an efficient way to find a Hamiltonian path. And I just like that example because it gives you two very similar and simple problems that seem to have some structure that we don't know that are very different. And so I say that, oh, this problem is easy and this problem is hard. But formally, when we say that an algorithm or the problem can be solved efficiently, we means that that the resource scaling of the algorithm or the way to solve the problem with respect to the size of the problem is like large or small. Maybe the important point here related to the last slide is that as I mentioned, we don't really think about a fixed size of problem. Like in the 7 bridges of Königsberg, the bridge, there are just 7 bridges, n equals 7. And if you can solve that problem, so like, so what? But the important, more interesting question is if you have a general graph, right? And then there's some parameter that signify the size of the graph, for example, like the number of edges or vertices. The question is, can you figure out an algorithm that is able to solve all instances of that in some time? And for example, okay, and we say that a polynomial scaling of this resource usually is time steps is efficient. So if you have a polynomial time algorithm, we say that it is efficient. So for example, here I can't really see anything from this. This is just a linear scaling. This is if the resource scale linearly with the size of the problem, such as n. Or maybe some algorithm you have like square root of n or log n or exponential of n. And this is the kind of thing that we have to look at when we think about complexity of the problem. And usually this scaling is given as an upper bound on runtime. Sometimes they use the big O notation. I'm not going to use it here. Even in the worst instance, as I mentioned. So for example, if they say, oh, an algorithm for multiplying two numbers runs in, I don't know, n squared, that means that the algorithm run in the asymptotic case. So for large n, the leading order of the runtime is n squared, and then you also ignore the constant in front. So maybe if the actual runtime is like 3n squared, and usually computer scientists doesn't care about the 3 in front. They just write down the scaling. So here I'm just giving generally the polynomial scaling is n to some constant c. So based on this, so computational complexity is a field that studies the difficulty or hardness of problems, of mathematical problems that's independent of like your computer, for example. For example, the famous two class of problem is P and NP. And the P is a class of decision problem that can be solved efficiently. So as I mentioned here, it means solvable in polynomial time. And decision problem just means that your answer is just yes or no. This is for simplicity. And there are some well-known problems that fall into this class, like multiplication of number of matrices. testing whether a number is prime or not, or some optimization problems with linear constraint. So this P is the class of easy problems. The more famous, the equally famous class of NP is sort of usually think of as a class of hard problem, although that's not really true because P is contained in NP. So NP just means a decision problem that if you are given a solution, a correct solution, you can check it in polynomial time, or you can check it quickly. For example, packing problems, maybe you are asked, well, if I have like 10 luggages, can I fit it into the back of your car, for example? Maybe you cannot figure out how to fit it in the back of your car, but if someone show you how to do it, like they just put it in and then it fit in the car, right? You can see immediately that that is a solution. And this is the kind of problems in the class NP. And there's a famous conjecture, is P equal to NP? Actually, if you can prove this, then you get it's like $1 million from Clay Mathematics Institute. And that means that, but actually and no one is able to prove this yet. But we strongly believe that P does not equal to NP. And this is the same as saying that, well, we don't believe that the ability to just recognize the solution will give you the ability to solve problem also. So I just put the quote here, is that if P equals NP, then the world would be a profoundly different place. There would be no spatial value in creative leaps. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Or everyone who could recognize a good investment strategy would be Warren Buffett. Let's say that basically in our world that we live in, it doesn't seem to be the case that just recognizing a solution, being able to recognize solution actually give you intuition about how to find that solution. Okay, I just give some concrete example of NP problems in terms of just equations. The famous problem of K-sets just asks you about if you're given some Boolean formula, whether there are variables that you can put in the formula and give you the answer 1 or yes, and this is called satisfactorability. So if there is some choice of variable like U1, U2, U3 that you put in, and then this Boolean formula evaluate to 1, then this would be or true. This would mean that this Boolean formula F is satisfiable. And there's some way, since I don't have time, maybe I just cut down on the formal definition a bit, but yeah, there's some problem called this satisfactorability problem, K-set problem that you can define. And this is probably a very famous so-called NP complete problem. In other words, it's like the hardest problem in NP, and formally meaning that if you can solve this problem, then you can solve any problem in NP efficiently. And actually there are about maybe like hundreds of NP complete problems. This is something that maybe in the in the 60s or in the 70s, these are something that sort of sparked this field of computational complexity when people found that, well, a lot of different looking problems are really the same. If you can solve one, you can solve the other. And so this kind of problem like K-set, as you given a formula, if there exists a solution, right? But note the asymmetry that if the problem asks you, if there's no solution, you wouldn't be able to tell, even if you can check a solution quickly, because to check that a solution satisfies a formula, you just check, right? But to say that a formula doesn't have any satisfiable assignment of variables, you have to check all possible assignments. And so this is just two different kind of statements. And I will summarize something like this, that NP problem formally asks you the problem of this kind, whether there exists something that makes some statement true. And then there's a different thing which is not really NP, but it asks you if for all of variables or something like this, is there for all variable this statement is false. This was just like summarize what I was just talking about in math. And well, why do I tell you this? Because this actually gives you a generalization of this class NP. So you remember there's a class P of easy problems. Sorry. And then there's class NP of hard problem, or it's like problems that are in NP but not believed to be NP are believed to be hard. And we don't believe that P equals to NP, so that means that NP, we believe that NP is strictly larger than P, but then you can keep playing this game. So for example, you can define a class above NP to be some like P level of NP, and this is, say that, so in the class NP, you define a problem by the quantifier exists here, but you can keep asking question that has like concatenate logical quantifier. Actually, this part may be a bit abstract, but yeah, but I just needed to define this polynomial hierarchy. And so the story is that you can keep defining just more and more complicated logical question. Like P, there's nothing. For NP, you ask if there exists something. And for a second level, you ask maybe if there exists for all such that blah, blah, blah. And then you can keep alternating, like if there exists, then, you know, the EA. And this actually gives you an infinite level of hierarchy called the polynomial hierarchy. And even though this is something unphysical, like we have no physical way to solve problems in this kind of class, you can still sort of conjecture the same way as P not equal to NP. The conjecture is that all of these infinite class are actually different. And people like to say, use the word that the polynomial hierarchy does not collapse. And actually beyond another fact is that you have these already really really difficult problems, but actually you have something over all this infinite level is even harder. It's called the sharp P, which is the problem of counting the number of solutions to NP problems. So for NP problem, you can like check ask you whether a solution exists, right? But for sharp P problem, it asks you for each NP problem how many solutions are there. And so it's at least as hard as NP, but yeah, it's actually seems to be a lot harder because there's this infinite tower between NP and sharp P. Yeah, so counting is hard. Okay, so finally we're back to quantum supremacy, and yeah, just look at the time. I have to finish in 10 minutes, so let's see how it goes. Okay. Yeah, so we're back to quantum supremacy, and I will just try to give you some little idea about how does what is the mathematical machinery behind this quantum supremacy thing, and it will involve those tower and sharp P. Okay, so there are many architecture or proposal for demonstrating quantum advantage, like the Google one based on superconducting qubits, the Chinese one based on light, and actually I have, you can't really read it, but yeah, this is one of my work with people in Poland and Hungary, and another Ph.D. student in Australia. We propose another scheme for quantum advantage or quantum supremacy similar to this one. But with the structure of that is like mathematically equivalent to some interacting fermions. So it's just some some new quantum advantage scheme based on some physics and cool math that physicists know. And really what you want to prove in quantum supremacy is the following. So you have a quantum device in the lab and which you can choose like what kind of circuit or program that you want to run, so what kind of utility you want to do, right? And then it just spit out some probabilities because quantum mechanics is not deterministic. So X here just means outcomes. So there's 2 to the n. If you have n qubits or n two-level system, you have 2 to the n possible choice of outcome that you can get when you measure. So I just represent this by a string. What you want to do in quantum supremacy argument is that we want to rule out all efficient classical simulator of this process. And a classical simulator would just mean that you have some classical device that when you input a description of this quantum program, it outputs some probability Q that is close to P. So it's some kind of noisy sampling. Okay, and I try to rush through this. So, so here is the recipe for proving quantum supremacy. And maybe this is something that as far as I can go in like 8 minutes, which was sort of an original goal anyway. So recipe for proving quantum supremacy, and this is something that like you have to do when you write a paper like what we wrote. So one is choose a class of quantum program. So this Q, right? Maybe it's anything that quantum mechanics allow you to do, or maybe it's some restricted set of utilities. And then now the rest is I divide into easy and hard problem. The easy problem is to show that approximating, this is just words, right? Show that approximating an ideal output probability P, this one is hard, is really hard in terms of the counting problem. And then the hard part is, I'm just like saying hand-wavingly that the hard part is to connect this point 2, what you prove here, to actually the problem of sampling, which is this is something that yeah, all of this that output probabilities only allow you to sample. And you know, when I write it like this, I say, oh, to write a paper, you just have to follow these 3 steps. It's like this kind of drawing guide. Like to draw an O, the first step is to draw 2 circles, and the second step is just draw an O. Yeah, and actually this hard part is something that we probably spend like 40 pages in our paper. But how does this work? Okay, how can I say this quickly? So the end goal actually, which connects to what I talk about complexity theory primer so far, is that all of this existing, well, most of this existing proof strategy is to finally show that the existence of an efficient classical simulator of a quantum process implies the collapse of the polynomial hierarchy. So, right, this is something that I talk about, this collapsing thing. That you have a tower of infinite number of complexity class that you don't believe that they're all the same, but if you can prove this, and if you believe that the polynomial hierarchy does not collapse, then it implies that no such classical simulator exists, right? Because this is just a contrapositive, right? If A implies B, then not B implies not A. Okay. Yeah, the rest is the argument that I'm not sure that I will have time to go through. So actually, give me a minute to think about. Yeah, not so many slides. Okay, let's do this. And well, how does that actually work? So this is like really the final piece of the whole thing of this talk is that let us ignore the sampling problem for a moment and just think about the hardness of calculating these probabilities, whether it be P or Q, whether it's the noisy one from classical simulator or the ideal one from the quantum device. Yeah, and so let's just say look at one of the probabilities. So the probability that you get the first bit out of the classical machine to be 1. So for a classical computer to output a probability, usually there has to be some random process inside, right? But classically, this randomness is not really that different from like deterministic process. You can have your computer produce some seed, some random seed that you don't know, and that actually determines. So this is like a pseudo randomness. You just have something that you don't know, and then you average over. And so this is just a statement that I want to make that for every classical machine that produces kind of probabilities, you can always model it as having some hidden bit string or hidden, if you like, hidden variables inside that when you average over actually give the probabilities that you want to know about. And actually the key point is that, counting this part, so to calculate this probability, you just sum up, so you average over this function that is a function of the real output, which is labeled as 1, and the hidden bit string R, right? And then I average over R. And so what I want to calculate this sum, I want to calculate, I want to find R bit string in which that give this function value 1. And that, well, if you like flip your head, think about it a little bit, is actually the same as basically evaluating like NP problems. The problem there's as if you have a solution and solution there's mean something that evaluate and then give you 1. So with some hand waving, I would say that counting this computational path that give you the final value 1, it's actually a Sharp-P hard problem. It's actually a Sharp-P complete problem. And so actually calculating exactly this probability, even from a classical machine, is extremely hard. How many minutes I have? 1 minute. Okay, so I guess without really explaining these 2 slides, basically there is an argument, an aspect of the easy problem in the proof of quantum advantage that just one thing that I want to bring up that relate to hidden variable, which is that actually if instead of exactly computing these probabilities, you just think of approximating. I'm not telling you the notion of approximation, but yeah, it's something worse than, it's something easier than exactly calculating this, right? And actually, classically in computer science, you can actually show that instead of exact counting, which is at Sharp-P, if you allow if you want to do approximate counting, this is actually very easy compared to Sharp-P. Even though it's not NP or P yet, so it's something that we cannot do physically, but it's in a low level of this polynomial hierarchy. And the reason that approximating counting is easy because there's a technique called Stockmeyer approximate counting, which basically what it does is grab the hidden variables, the hidden bit string, and then do some manipulation with it to give an estimate of this the counting or the probability. And that is something that you cannot do in quantum mechanics or quantum theory because there's no really no hidden variable. Yeah, just ignore this. Yeah, it's just in the complexity is very different. It's just in the low level of polynomial hierarchy. Yeah, so back to this recipe. Yeah, the hard problem that I didn't tell you about is the following. Okay, so step 1, step 2, right? Step 2, the easy problem is to show that the output property of approximating the output property of a quantum device is hard. And then the hard thing to show is really to show that approximating this classical probability, which we show to be, we didn't show, which we see that is still hard, but it's a lot easier than exactly calculating px. You show that this approximating of q actually lets you approximate p as well, the ideal quantum probability. So maybe to say it in word is that the hard problem to show quantum advantage is to show that approximating the output property of a classical machine lets you approximate the output property of a quantum machine as well. But the latter test turns out to be actually really hard. It's still sharp P, which is what we have to show in the first section, right? I mean, so what happens is that we use some solution that we get in the lower level of polynomial hierarchy to solve a problem that is extremely harder. And this is called the collapse of the polynomial hierarchy. You just squish the infinite level to some finite low level. And as I mentioned, well, this is not the message, but if we don't believe that the polynomial hierarchy collapsed, this would complete the proof that there does not exist a classical machine that can simulate your choice of quantum machines. And heuristically, the reason is that there's no hidden variable to grab in a quantum machine. All right, okay, so I'm done. Yeah, maybe it's just a summary. So yeah, take home messages. Provable quantum advantage are designed to be provable by the name with available mathematical techniques, although they may be useless. But as I mentioned, well, it's actually not really useless. Another message that actually proving quantum advantage is really about proving the limitation of classical information processing. And you might realize by now that I barely talk about anything quantum in this talk. It's all about thinking about what is the real limitation of a classical world, classical information processing. And with that, I just leave you with the last slide, and I will just take any questions. There's just some propaganda for people who may be not interested in quantum information, but interested in something else. But maybe quantum information show up as well in those fields. Thank you.
Thank you, Dr. Ninnat, for a great talk. Does anyone here have a question? Does anyone have any questions? You can.
I have some questions for the problem of the bridge you mentioned. Mm-hmm. If we would like to solve the problem classically, up to my understanding, we have to compute all possible way to cross the bridge, right?
So for the bridge, right? Actually, so Euler proves something that you can. So if the problem just asks whether it exists a path, actually Euler proves some theorem, some simple thing that you can check, like whether there's even number of edges or something like that. So actually you don't have to in the bridge problems. But
and what the advantage in a quantum picture?
For this one is well, there's really no advantage because the problem's already solvable quickly with the classical computers.
I mean, if you apply the quantum idea to this problem, I mean you do the same thing as classical or something different?
Yeah, you do the same thing as classical. Yeah, but maybe in some optimization problems like not really optimization problem, but in some problem like that I mentioned, the other problem from the bridge, right? Like walking on some dodecahedron shape, that one we don't know an efficient classical algorithm, and maybe a quantum algorithm can help. I mean, usually the no-brainer way is just to use some Grover search to just reduce the number of search space. But I mean, there's some details. It doesn't always help you, but yeah.
Thank you. But at the moment, I'm not understand about the quantum quantum philosophy you talk in the seminar. I'm not. What is that? Can you explain very simple picture? What is the difference between quantum and classical?
You mean computer algorithm?
Yes, algorithm.
Yeah. So for quantum algorithm, so basically you are allowed any operation that is allowed in quantum mechanics. For example, you can use superposition or entanglement. Even though at the end you still have to measure at the end. So like you cannot do something like try out all possible solutions and then get all of them. You can just one at a time. But in the process, it depends on the problem. You have to design the algorithm so that the interference kind of, I guess one simple way that I have, like someone said in one sentence, is that quantum computing is about destructive interference of wrong solutions.
Okay. But you have to find how.
Yeah, usually.
Okay.
Yeah, usually we're pretty specific to the problem.
Okay, I get something. Thank you.
Okay, any further questions? And there is no question from the audience online. So I think I would like to end this seminar for now. And thank you, and let us thank you for the speaker, and thank you for all of you for participating in this seminar. Looking forward for you to joining to the next seminar. Thank you.